Hello and welcome again to the next lecture on terpenoids. Today we will discuss on a bicyclic sesquiterpenoid. The name is Santonin. We will discuss on its occurrence and uses, structure elucidation, synthesis, reactions of Santonin, and finally the stereochemistry of Santonin, which is very important. First of all, introduction of Santonin. It is obtained from the dried unexpanded flower heads of Artemisia, which is also known as worm seed, and it is found in Asia. Its uses is it is widely used in medicine as an anthelmintic. Anthelmintic means it is a very useful medicine to expel out the intestinal roundworms. Next we come to the structure determination of Santonin, which is based on the chemical analysis. The steps are as usual. First of all, the molecular formula. From elemental analysis, it is shown that the molecular formula of Santonin is C15H18O3. From this, the number of carbon atoms is 15, which gives very useful information about the fundamental structure of Santonin. First, it belongs to sesquiterpenoid class of compounds as it contains 15 carbon atoms. And secondly, according to special isoprene rule, the 3 isoprene units are joined in head to tail fashion. The third important information is achieved from this molecular formula is the degree of unsaturation, which is given by the following formula, and keeping the values of x and y from the formula, we get double bond equivalent equal to 7. This means these 7 either double bonds are present or it is a cyclic structure. Rings are present in the molecule. Next we come to the type of unsaturation, that is the nature of unsaturation, which gives information about this 7 double bond equivalents. It is done as follows. Santonin is subjected to hydrogenation using a catalyst, and it forms tetrahydrosantonin. This tetrahydrosantonin, as you can see, the difference in the molecular formula is of hydrogen atoms is of 18 and 22. This means 4 hydrogen atoms. It means 2 molecules of hydrogen atoms molecules are being consumed, and we reach to the conclusion that it contains 2 double bonds as 2 molecules of hydrogen are consumed. Next we come to the nature of oxygen. First of all, we should know that it is a neutral compound, neither acidic nor basic. And the nature of oxygen, we have to take the nature of oxygen of 3 atoms. That means it contains 3 oxygen atoms. With this, it can be done by the following reaction. Santonin dissolves in alkali to form the salt of hydroxy acid. This is santonic acid. The formation of santonic acid gives very useful information about the nature of the oxygen atoms. This hydroxy acid can be formed probably from the lactone type of ring, because lactone type of ring on hydrolysis with sodium hydroxide, it forms a hydroxy acid like you can see here. So the most probably the structure this of Santonin contains a lactone type of ring. So 2 oxygen atoms are being consumed. As you can see the conclusion, Santonin is a lactone. This can also be further verified by IR spectra. IR spectra shows a carbonyl band at 1770 centimeter inverse, which is a characteristic of saturated gamma lactone. This means a gamma lactone type of ring is present in Santonin. There is one more oxygen atom. We have only verified the 2 oxygen atoms. There is one more oxygen atom in Santonin, and it can be subjected to chemical analysis to show the nature of this oxygen atom. And Santonin forms oxygen with hydroxylamine, as you can see. This is a characteristic reaction of carbonyl containing compounds. This means one carbonyl group is present in Santonin. Santonin contains a carbonyl group. This is the conclusion of the above chemical reaction. It can also be verified by the UV spectrum. UV spectrum of Santonin shows lambda max at 236 nanometer and its epsilon max value is this one. Conclusion can be drawn that the carbonyl group is the form of alpha beta unsaturated ketone. This lambda max is the characteristic value for the alpha beta unsaturated ketone. Thus, up till now we have reached to the following conclusions. The molecular formula of Santonin is C15H18O3. Its double bond equivalent is equal to 7, which corresponds to 2 carbon-carbon double bonds, 1 lactone ring corresponding to 2 double bond equivalents, that means 4, and 1 keto group is present also. This corresponds to double bond equivalent. Means up till now we have justified the 5 double bond equivalents. 2 double bond equivalents are still left. Next we come to the carbon skeleton of Santonin. This can be verified. This carbon skeleton can be verified with this reaction with zinc on this Santonin on distillation with zinc dust. It gives a mixture of 1,4-dimethyl naphthalene, 1,4-dimethyl naphthol and propene. The formation of these products suggests the presence of naphthalene structure in Santonin. As you can see, naphthalene structure in Santonin, which corresponds to 2 double bond equivalents, which means that 2 rings are present in Santonin. Just you can see there, one we have also justified the 2, the naphthalene skeleton or 2 rings are present, so it gives a total of 7 double bond equivalents. Next very important structure determination point is the presence of 7-ethyl 1-methyl naphthalene structure in Santonin. As we have to now justify the positions of double bonds, the position of lactone ring and the position of the methyl groups present in the Santonin. As you can see, the Santonin on catalytic hydrogenation, it forms tetrahydrosantonin, which on reduction, Clemenson reduction, it yields deoxy-tetrahydrosantonin. That means the carbonyl group is converted into CH2 group. On selenium dehydrogenation, it yields this type of hydrocarbon. The name is 7-ethyl 1-methyl naphthalene. This 7-ethyl 1-methyl naphthalene is also obtained from another formula. Further reduction of this tetrahydrosantonin, it forms hexahydrosantonin, or you can also we can also do the hydrogenation directly also, leading to hexahydrosantonin, which on selenium dehydrogenation yields the same naphthalene structure, as you can see. And the formation of this naphthalene structure corresponds to 13 carbon atoms which is present in Santonin. That's the conclusion you can see here. This indicates the presence of this skeleton in Santonin, and the presence of this skeleton forms that 13 carbon atoms are present. Now we have to assign 2 more carbon atoms, which we can also do during hydrogenation. This is an actual fact that during selenium dehydrogenation, angular methyl, very important thing you should note this, angular methyl and carboxyl groups are lost. This means we already know that the lactone ring is present in Santonin, which might have converted on selenium dehydrogenation, it might have converted into carboxylic acid, which is lost during selenium dehydrogenation. This corresponds to 1 more carbon atom which is present in the form of lactone ring. 1 more is also we have to assign. Might be the probable condition is that an angular methyl group may be present in Santonin, which during dehydrogenation might have been lost. So we have assigned two more carbon atoms, C13 already, but it contains C15. We have assigned the probability that might be one in the form of carboxylic group and other in the form of methyl group, but we have to justify this with some chemical analysis, which is done in the further point. This is next we come to formation of and structure determination of hyposantonin. It is a very important compound which is formed from santonin, and it gives very important information about the structure of santonin. Santonin on reaction with hydroxylamine, as we have already read, it forms oxime, which on reduction with zinc and H2SO4 it forms santonamine. This means the oxime form part has converted into an amine, on which on reaction with nitrous acid it forms hyposantonin. This hyposantonin is subjected to chemical analysis. Structure formula is determined and its double bond equivalent is also equal to the santonin, which is 7. Now let us see the structure determination of hyposantonin. We will go very generally. First, it converts KMNO4 oxidation converts it into dicarboxylic acid. 3,6-dimethyl phthalic acid is formed from hyposantonin, and this reveals the presence of the ring structure which has been degraded during oxidation. The second is reaction with iodine and acetic acid. The electron ring might have been broken here with iodine and for resulting in the formation of santanic acid, as you can see here, and resulting in next the barium hydroxide reaction. As you can see, the structure is this type of structure is obtained. The same structure is obtained from HCl and ethanol also, as you can see, and reaction with barium hydroxide leading to the same structure. This means you can see very well here that the position of two methyl groups are the same in all the reactions. This means we can assign the position of the two methyl groups in hyposantonin, as you can see in the next slide. As you can see in this slide, this is hyposantonin. We have assigned the structure of hyposantonin here, and from this you can see the reactions HCl and ethanol. This is dihydrosantonic acid, which is being found. We have assigned the assigned the position of hyposantonin in these two cases, and the reaction gives this barium hydroxide. It gives this type of structure, as you can see here. From the basis of this hyposantonin, we can also assign the structure of santonin, as you can see in this slide. This is the structure of santonin based on hyposantonin. As you can, we have taken the possibility of selenium dehydrogenation here, and we have assigned the position of one methyl group in this position. This angular methyl group is present, which have been lost during selenium dehydrogenation. So this is the electron ring. On the basis of this we have assigned, and this structure reveals all the reactions that we have studied earlier. As you can see, the sodium hydroxide reaction with sodium hydroxide, it is forming carboxylic acid, which reveals the presence of a electron ring. Zinc distillation, as you can see, the three compounds as we have already studied, and you can see here the reactions of santonin with hydroxylamine yielding oxime, and with zinc and sulfuric acid it forms santonamine. This carbonyl oxime group is reduced into amino group. Similarly, the catalytic hydrogenation, as you can see, the formation of tetrahydrosantonin, hexahydrosantonin, and the reduction with on the upper side you can see the Clemenson reduction, conversion of this carbonyl group into CH2 group yielding deoxy-tetrahydrosantonin, and with selenium dehydrogenation it forms 7-ethyl 1-methyl naphthalene, and similarly the catalytic hydrogenation complete, it forms hexahydrosantonin, and with selenium dehydrogenation it forms 1-methyl 7-ethyl naphthalene. Thus, by assigning this structure, all the reactions and the final products have been explained by this santonin structure, so we can easily assign this santonin structure. This final structure of Santonin has been confirmed by synthesis. As you can see, the starting compound we have taken is this carbonyl compound, alpha beta unsaturated carbonyl compound, here this is Michael addition with this malonic ester. This undergoes rearrangement, and the addition of this Michael addition takes place at this carbon atom. As you can see here, this Michael addition is stereospecific reaction, and malonic ester group, it occupies the most preferable equatorial position in this cyclohexane ring, as you can see here, which on conversion, the reaction with selenium oxidation, it forms this type of compound, and resulting in the formation of, you can see double bond here, resulting in double bond here, and the reaction with sodium hydroxide and hydrolysis and heating, it yields this type of compound. As you can see, hydrolysis yields convert it into carboxylic acid, and finally acidic hydrolysis and heating leads to decarboxylation, resulting in the formation of this type of compound. Finally, on selenium oxide, it forms alpha and beta Santonin. This is the method preparation for the alpha and beta Santonin. This carboxylic acid which is being formed, it is a racemic mixture of both alpha and beta Santonin, which subsequently the alpha form of this carboxylic acid yields forms the alpha Santonin, and the beta form of this forms the beta Santonin. Next we come to very important reactions of Santonin. First of all is the Santonin. On reaction with nitrous acid, it forms hyposantonin. As you can see here, hyposantonin. This involves a very important rearrangement, as you can see here, involving an electrophile. This nitrosonium ion have been formed with the nitrous acid. This nitrosonium ion reacts with amine here, resulting in the diazotization process. As you can see, these are all the diazotization process which have been formed. Finally, this nitrogen which has resulted in this nitrogen can be easily, it's a very good leaving group, it expels out from the compound, resulting in the rearrangement and formation of, you can see, resulting in the formation of secondary carbocation. This undergoes Wagner-Meyer-Win rearrangement, that is 1-2 shift, resulting in the formation of more stable tertiary carbocation, and which on the resultant or expulsion of proton forms the hyposantonin. So the driving force for this Wagner-Meyer-Win rearrangement is the formation of a more stable aromatic ring. Again, such type of rearrangement is also found in dienone phenol rearrangement. As you can see, Santonin in the presence of acid, it undergoes rearrangement and forms demotropose Santonin. This demotropose Santonin has been formed by the same as we have studied, same type of rearrangement as we have studied. As you can see, this is dienone. Santonin contains dienone type. In the presence of acid, it again undergo protonation, as you can see, and then this rearrangement takes place, rearrangement resulting in the formation of this carbocation. This carbocation again undergoes Wagner-Meyer-Win rearrangement, as you can see, 1-2 shift, resulting in the formation of a more stable tertiary carbocation, which then undergoes deprotonation, yielding demotropose Santonin. Okay, this is also known as dienone phenol rearrangement, very important reaction of Santonin. These rearrangement reactions made scientists very difficult for the structure determination of Santonin due to its facile rearrangement. Next or last, we come to the stereochemistry of Santonin. As you can see in the structure, it contains 4 stereo centers or chiral centers are present, and the naturally occurring alpha and beta Santonins, as you can see the structure, the difference in the structure is at C11 epinal, that means it is a C11 epinal. The difference between alpha and beta Santonin results from this carbon atom. As you can see, this is alpha Santonin, it has S configuration, and this is the structure of beta Santonin, it has R configuration. That's all. Stay safe, stay healthy. Thank you.